Hi everyone! In this demo, we'll walk through an example of hyperparameter optimization, or HPO, on Azure ML using GPUs and RAPIDS to accelerate model training. Basically, HPO will explore many different parameter choices and then choose the combination that leads to the best model. This is a simple and automated way to get a more accurate model without writing new code. But the challenging part of HPO is that it can take a really long time since you train so many model variants. And so what we'll see in this demo is that RAPIDS can reduce model training time by 25x, which would allow you to train dozens of models in the same time that it would take to train a model on CPU. And so these are the main parts of this demo. We'll first use the Azure portal to set up all the resources we need to run this job. Next, we'll set up our local environment and run a notebook locally to orchestrate that job. And then this notebook will launch a Docker container on Azure to do all of the heavy lifting, so you don't need a local GPU or data. And all the material that I referenced today is also available in this GitHub repo on RAPIDS.ai/CloudML examples under Azure. Alright, let's get started. First, we need to create a subscription or access information from an existing one through the Azure portal. So if I go to the portal, under All Services, we can click on Subscriptions to get the name and ID of the one we want to use for this demo. I've already created one that I'll use. Then we'll create a resource group, or again, you can use one that you've created before. For this example, I'll just create another one. So again, here you can select your subscription, then add a name for this resource group, for example, Azure Demo, and then choose a region with GPU resources. I'll pick South Central US, for example. I've also linked 2 pages for the list of supported regions and information on GPU VMs and the README of the repo that I showed earlier. Okay, go ahead and create this. Next, we'll create a machine learning service workspace in this resource group. So if we go back to that resource group and then click on Add, here on AI plus machine learning, and then click on machine learning. Here again, we can select the subscription and resource group, and then add a workspace name. For example, Azure Demo HPO. Select a region, South Central US, and then Workspace Edition. All right, let's create this too. This will take a bit longer, about a minute, and we'll see a deployment is complete message after it's created successfully. The workspace was just created, plus some resources associated with it like credentials and storage account for outputs and logs. Alright, let's go to this workspace and download the config file. We'll copy this file to the same location that we'll be running the notebooks from. This will load the workspace details using AzureML SDK. So we've set up our workspace on Azure. Now I'll set up my local environment and launch the notebook example on my local machine. Here's my terminal. I've created a Conda environment, named it AML Demo. I'll activate that. I've also installed AzureML SDK and then cloned the CloudML examples repo from RAPIDS AI that I mentioned at the beginning. Let's look at the notebooks folder under Azure. I've copied the config file that I downloaded earlier. We'll use this in a bit to load the information from this file and the initialization step of the notebook. All right, let's launch Jupyter Notebook and open a web browser to access these examples. Here's the HPO RAPIDS notebook. First, let's verify that we've installed the AzureML SDK. Okay. So the next step, you can either download a sample dataset that we've uploaded to public data store if you want to test the same data that we're using for this demo, or you can use your own dataset. Either way, we'll upload this in a bit to the default data store of this workspace. Okay, so here's where you can use the config file to load and initialize the workspace that we just created. Here's the workspace name, the region that we selected, and the resource group. And then my data is actually in this local folder called airline 20M, which is 20 million rows of the airline dataset in Parquet format. And I'll upload it to a path on this default data store, for example, airline data. And after that, we'll create a compute target using AzureML Compute for training our model. Here's where we add VM size to specify VMs with GPUs that are supported by RAPIDS, which is Pascal or newer GPU architectures. I've listed VMs with P40 and V100 GPU in the README of the repo too. So here I'll use VMs with 1 Volta GPUs. And then maximum node is actually the number of nodes that we'll use for hyperparameter optimization. We'll get into more details further in the notebook too. Okay, let's go ahead and create this GPU cluster. Then we'll create a local folder to copy the code that we'll need to access on the remote compute, or in this case, GPU cluster. These are training scripts that we've provided in the repo under code folder. And for example, train RAPIDS Python script will be used for the entry script of our estimator. You can look more into these scripts if you're interested, but we'll dig deeper into data science piece in future videos. But basically, at a high level, what this will do is there are steps to load our data set into GPU data frames using cuDF, and then train with random forest on a GPU using cuML. Okay, so we've prepared the data and training script, almost ready to train on the remote cluster. So next, we'll create an experiment, for example, train RAPIDS, to track all the runs in our workspace. This will be useful once we start training, and we can use it to monitor our runs in the UI later. After that, we'll create an environment. In this case, we'll use a RAPIDS Docker image with RAPIDS 0.14, and then we'll also install AzureML SDK and AzureML widgets. This can actually take about 10 to 15 minutes once we submit the job, but only the first time you run it. So the image will get added to your Azure Container Registry and then cached the next time you run this experiment, as long as you don't change the environment and it stays the same without any modifications. All right, then we'll create our RAPIDS estimator using the environment that we just created. The source directory here is the folder that includes the training scripts, and then the entry script here is the script that's used for training. We'll also mount our Workspace's default data store here, which includes the data set that we uploaded. Okay, and so now we'll configure our hyperparameter tuning experiment. We can define the hyperparameter space to sweep over. We've chosen 3 parameters here with random sampling to try different parameter configurations and find the one with highest accuracy for our random forest classifier. So maximum depth here is the depth of each tree. Maximum features is the number of features to look at every time a node gets split. And then the number of estimators is how many trees we're actually going to build. The primary metric can be defined here in metric name and metric goal, which will be used for optimizing the hyperparameter tuning experiment. So in this example, we used accuracy and we want to be able to maximize that. And then maximum total runs is the maximum number of training runs that'll get created. And maximum concurrent runs is the maximum number of concurrent or parallel runs, so the maximum nodes that we added when we created our GPU cluster. All right, now we're ready to submit this experiment. And we can actually monitor it and view the progress of these jobs using the AzureML notebook widget. So this will take about 40 minutes to build the image, push to Azure Container Registry, allocate GPU resources, and complete the HPO job. So for the purpose of demo, we chose a fewer number of nodes, but for a more realistic and closer to production run, we can actually change the total runs here, for example, to 100 and 10 concurrent or parallel runs. That will take about 2 hours to run with RAPIDS on GPUs. And with the same configuration, it will actually take 2 days to run on CPUs with Scikit-learn to complete this hyperparameter sweep. So this shows that we can reduce the time it takes to tune our model from days to hours, and overall it will actually reduce our total cost too. So while this is running, we can also look at the details of the experiment. If we open this in another tab, we'll see the experiment name here. And then we'll see the name of our cluster, the total number of runs, maximum concurrent runs, the primary metric, the goal. So basically we want to maximize our accuracy. And these are also all the available parameter options. So once the job gets created and the child run here, we'll see all those runs with the number of each of them. And then also the outputs and log of these will get added too. And then we can see for each of those, for example, what was the accuracy, the number of estimator that was chosen, maximum depth, features, and so on. So we'll come back and look at this once the job Alright, so the HPO job has completed, and this table shows the child run number, accuracy, status, how long it took to load the data, train, and run inference. And then the chart below that shows accuracy for each of these runs. So if we click on each of these or hover over them, we can look at that particular run and the corresponding accuracy. There's also this parallel coordinates chart that shows information about all the hyperparameters for these runs. For example, the highest accuracy is yellow, so we can look at this and find the number of estimators, maximum depth, and features that actually resulted in that particular accuracy. There's also 2 other options to look at: 2D scatter chart and also this 3D chart. And again, we can look at all the information for each of these runs. So if we go back to the UI, we'll see a similar chart, similar to the 2D scatter. And then this shows how accuracy varies with different parameters. We'll get into more details of the training scripts and GPU libraries that were used in this demo in future videos, as well as how to load data and train on multiple GPUs using DAS. And finally, check out the HPO webpage on rapids.ai. So if we scroll down, here it is. and we can actually see these charts that are results of the demo that we just went through, but with 100 runs that I mentioned earlier. You can also find more information about RAPIDS integration into different cloud services and distributed frameworks.